Professor Srivastava, do you hear us?
Yes, sir. Sir, I want to correct that I am not professor, I am scholar. I am present and I can present my works if you
Okay,
allow me.
sure.
So may I share my screen?
Yes, we see you now.
Yes, sir. Okay, sir. Fine.
So let me present your title. Professor Srivastava Vivek Kumar is going to talk on exponential corrections to the thermodynamics of charge quasitopological rotating black holes. Actually, this is a very interesting and trend topic nowadays in the literature. So this is your turn.
So may I start, sir?
Yeah, you can start, but we don't see your screen. Only we see you. Yes. It's gone.
Sir, is it visible? So my slide is visible, sir?
Just a minute. I just see you, not your screen. Maybe because of view now. Professor Behnan, do you see his presentation? Because I don't see. I only see himself.
No, we can't see.
No, we don't see.
Yes.
Now it's okay. Yes, now. Okay.
Okay.
Continue, please.
Sir, changing, sir. Please confirm one thing more.
Now everything is fine. You can continue.
Okay. Thank you very much. A very good evening to all of you. I am Vivek Kumar Srivastava from Rajju Bhaiya Institute, Veer Bahadur Singh Purvanchal University, Kanpur, India. Express my heartiest gratitudes to the organizer of Third International Conference on Holography and its Application 2024 for providing me an opportunity to present my work entitled Exponential Corrections to the Thermodynamics of Charged Quasitopological Rotating Black Hole. This work is being non-perturbative corrections to the thermodynamics of quasi-topological black hole, which is under process. And this work is in collaboration with Dr. Srivastava and Dr. Kumar. These are the outlines of my presentation. First, I would like to bring out the topology of quasi-topological gravity. The class of gravitational theory in which we are having the action as a topologically invariant is a topological gravity, and it does not depend upon the metric while it depends upon the global property of the matter. The local degree of freedom it does not contain, and it is used in the study of quantum field theory, topological field theory, etc. The end class is quasi-topological gravity, which is extreme general theory of relativity, where we are having the action which includes the higher order creature invariant term added with an Einstein-Hilbert action. This quasi-topological gravity includes the local degree of freedom, and it is used in the study of high-dimensional theories, black hole physics, ADS-CFT correspondence, etc. For the study of higher derivative gravity theories, the first generalization is by addition of the Gauss-Bonnet term. This Gauss-Bonnet get added with the higher derivatives, but this Gauss-Bonnet terms contains only single coupling constant. Due to this one coupling constant, this Gauss-Bonnet terms is not sufficient for the duality theory. This Gauss-Bonnet terms remains limited for the study of dual theory. To improve this limitation further, it was included by the addition of third order level of terms whose equation of motion is of second order differential type equation, but this third level of term also do not contribute to the field equation in the case when we are having the 6 or lower dimensional space time. The cubic term vanishes due to the topological origin of the Euler density in 6 dimension. Further on, in sight of removing such discrepancy, the new interaction was proposed, which includes both the Gauss-Bonnet term as well as the curvature cubed interaction term. This curvature cubed interaction term do not contains the topological origin as it was in the case of Lovelock gravity, hence it was proposed as the quasitopological. The properties of quasitopological gravity are such that the equation of motion is of fourth order derivative, and in the case of spherically symmetric space-time, we are having the equation of motion. We are having equation of motion as a second order derivative. The exact black hole solutions for the quasitopological gravity also exist. As we know that the black hole entropy is proportional to the event horizon area. Typically, this black hole entropy is what horizon area. The black hole can be classical mechanically as well as quantum mechanically. But on discussing the quantum mechanically, this black hole emits the radiation, which was termed as the Hawkins radiation. Because this Hawkins radiation, the size of black hole decreases, which may lead to the evaporation. At the quantum ground level state, the black hole may stop the evaporation and it may increase the stability. To study the black hole at quantum scale, the study of thermal fluctuation is one of the best methods. With the decrease in the size of the black hole because of the Hawkins radiation, the logarithmic and second order perturbation terms provides a perturbative correction for the black hole entropy. The correction for the logarithmic term was for the quasi-topological black hole gravity was also done with one of my collaborators, sir, Dr. Sudhakur Upadhyay sir, and in this work on the further reduction, we are having the non-perturbative analysis due to the thermal fluctuations. The exponential term get added with the non-perturbative corrections for the black hole entropy, which is negligible for the large horizon radius. The entropy get exponentially corrected when we are having the micro state countings performed at the quantum scale on the horizon only. The total correction of the entropy for both the perturbative and non-perturbative corrections is given by equation 2.1, where S0 provides the original entropy without any corrections, and second and third terms will provide the perturbative correction, and last term will provide the non-perturbative corrections. To study the non-perturbative corrected entropy, we are having equation 2.2. As we discuss about the quasi-topological gravity, the general action for n+1 space-time dimension is given by equation 3.1, where R is the Einstein action, lambda is the cosmological constant, defines as a function of dimension and ADS radius, where Z and Z3 are the Gauss-Bonnet terms and quasi-topological terms, which can be as a function of chi2 and chi3 respectively, where chi2 and chi3 is given in equation 3.4 and 3.5. When we include spectrometric field, this action get modifies in the form of equation 3.6, where we have an term of 1/4 F mu nu, which is defined as the Maxwell tensor in terms of vector potential. This provides the metric as in the form of equation 3.7 for the rotation parameter k, which is a function of Laplace function and metric function. The metric function is defined in equation 3 for a range of angular coordinates given by 0 to 2 pi. Rho is defined in the form of equation 2.9, which can be further simplified in the angular velocity of Killing vector. On solving this metric, we are having the integration constant as a mass, which is defined in the form of equation 3.1. Proceeding further on following the standard method of analytical continuation of the metric, one may obtain the temperature of the event horizon as a Hawking temperature in the form of equation 3.11 in the form of electric potential phi, which is given by equation 3.12. Based on these evaluations, the uncorrected entropy of a charged rotating quasi-topological black hole in the absence of any thermal fluctuations using the Gibbs free energy and Hawking temperature is given by equation 3.13. From this, we calculated the non-perturbative corrected entropy per unit volume as in the form of equation 3.14. The variation of entropy density with respect to the horizon radius for 3 plus 1 space-time dimension is shown in figure 1. For this variation, one may observe that this entropy density variation is monotonically increasing function, which corresponds that in the range of lower horizon radius, we are having the positive corrected parameters as positive entropy, and for the negative correction parameters, we are having the negative entropy in the range of low horizon radius. While we are moving towards the large horizon radius, this non-perturbative correction is insignificant, and and for all the corrected and uncorrected entropy, these variation get converges. Based on these evaluations using the corrected entropy, which is non-perturbative corrected entropy, and the Hawking temperature, we evaluated the internal energy of a charged rotating quasi-topological black hole as in the form of 3.15. The variation of internal energy with respect to the horizon radius for 3 plus 1 space-time dimension is shown in figure 3. In figure, from this variation, we observe that we are having a critical point. We are having the positive asymptotes for the negative value of the correction parameters and the negative asymptote for the positive value of the correction parameters. While as we move towards the large horizon radius, we are having a converging of the both corrected and non-corrected parameters. We also observe that we are having the variation of positive corrected parameter and followed by the uncorrected internal energy of the charged rotating quasi-topological black hole. Next, we calculated the Gibbs free energy per unit volume for the charged rotating quasi-topological black hole with the use of Hawking temperature and the non-perturbatively corrected entropy as in the form of equation 3.16. From this, we are having the variation of this Gibbs free energy with respect to the horizon radius for 3 plus 1 space-time dimension, in which is shown in figure 3. From this variation, we observe that we are having the positive asymptotes, the positive correction parameters, and the negative asymptotes for the negative correction parameters in the range of lower horizon radius. While as we move toward the large horizon radius, these variations get converges. For this charged quasi-topological black hole, we also calculated the total charge density. The total charge density can be evaluated as in the form of equation 3.17. From this equation, we observe that the total charge of this charged rotating quasi-topological black hole does not exist for the dimension less than 3 plus 1. The variation of charge density with respect to the horizon radius for 3 plus 1 dimension is shown in figure 4. For this variation, one may observe that with the uncorrected with the uncorrected charge density, we are having the independent behavior of the total charge in whole range of the horizon radius. While in the lower range of the horizon radius, the positively corrected parameters provides the negative value, parameters provide the positive charge value. We also calculated the charge of rotating quasi-topological black hole, which incorporates the angular momentum and evaluated as in the form of equation 3.18. The charge density, which is a function of extensive parameters such as entropy, angular momentum, charge of charge rotating quasi-topological black hole, can be evaluated as in the form of equation 3.19, which is plotted in figure 5 of 3 plus 1 space-time dimension. From this, we are having the conclusion that in the lower range of horizon radius, for the positive value of the correction parameters, we are having the negative mass value. For the negative value of the correction parameters, we are having the positive asymptotes. As we move towards the large horizon radius, the variation get converges, and at large horizon radius, this correction parameters does not provide any significant help. It is also observed from this region that the variation of positive correction parameters is as similar to the variation of the uncorrected parameters. The stability of the black hole thermal fluctuation is based on the analysis of the signature of the specific heat. To study the stability and the phase transition of the system, we evaluated the specific heat of the charged rotating quasitopological black hole, which can be found in the form of equation 4.1. From this, we are having the variation of the specific heat with respect to the horizon radius for t plus 1 space time dimension in the form of figure 6. From this variation, we are having a critical point, let's say at r plus equal to r. Below this critical point, we are having the negative value of the specific heat. As we move forward from the critical point, we are having the positive specific heat. From the solution of this 4.1, we may also obtain the bound points with respect to the horizon radius. From these analysis, we may observe the negative value of the entropy correction parameter is not physically significant, therefore it can be forbidden. We also observe that with the change of the dimension of the space and as well as the radius, we do not have any significant change in the nature of the variation. One may also observe that the initial correction have only significant change in the lower horizon radius, while in the range of the large horizon radius, this non-perturbative collection parameter does not provide any significance. We are also having the negative value of specific heat below the range of the specific critical point. From this, we observe that in the range when we are having the negative value of the specific heat, this shows the instability of the system, and as we move from the negative to positive value of the specific heat, we are having a phase transition, and we move from an unstable state to the stable state in the region where we have the positive value of the specific heat. Thank you.
Thank you, Srivastava. Do you have any questions?
Hello,
Hello? Yes.
Professor Sakali, can you hear me?
Yes, we hear you. Please continue.
I have a question for Mr. Srivastava.
Sure.
Mr. Srivastava, can you go back to the heat capacity here? Okay, so
Yes, sir.
what you're talking about is essentially a black hole, quasi-topological rotating black hole, and the corrections are quantum corrections, right? Exponential corrections. I have seen many
Yes, sir.
papers in the field. I mean, it's being very rigorously discussed these days. So I'm just wondering on the physical picture of what's really happening over there. So because the heat capacity, you can see it crosses through two zeros actually. One is when the event horizon goes to zero, that's the complete elimination of the black hole, Hawking evaporation. And before that, you have one more zero actually. So there are two routes actually. So my point is actually, if normally when heat capacity goes to zero, this essentially means the black hole stops evaporation, right? So what's actually going on here?
Yes.
I want to really understand, please help me to understand, if at a certain finite radius around 0.7, I think, it goes to zero, shouldn't black hole stop there altogether? Why would it continue evaporation? I mean, the heat capacity is saying, I mean, it's conveying this, giving this sense out, actually. I just want your remarks on that. Please help me to understand.
As we are in the range of negative value of the specific heat, as we are in the range of negative value of specific heat, we are having the instability condition. And as we move toward the positive value of a specific heat, there is a transition from the instability to the stability region, where we may attain the stability. And since this black hole is unstable because of the you may say that the Hawkins radiation is the because of the evaporation, and which may provides the state where we are having the stability phase.
Okay. So here it seems these two zeros are independent of quantum parameter, right?
Sorry?
The roots of heat are independent of quantum parameter.
Hello?
So just a minute.
Could you hear me?
Yeah, could you repeat your question
Can you
again?
My question is actually, I mean, here what Vivek is saying is like this could be present even for the black hole with eta equal to 0. You can see in the figure the black hole. So you mean to say the negative region still exists even we have eta equal to 0, right? The stable region, I mean to say. Sorry, the unstable region. C negative.
Yes, sir. In the range of lower horizon radius, we are having a negative value.
So that means the black hole is unstable in this regime, right?
Yes. This black hole is unstable. This black hole is an unstable.
Yeah, as far as I know, I mean, the heat capacity, usually the zeros of heat capacity indicate whether the black hole has come to an end or not. So we have two zeros here. If it already crosses the first zero, why would it continue still within an unstable regime? I struggle to understand these points. So can you please help me to understand?
Sorry, sir, I don't have any particular idea about this.
Okay, it's fine, no problem. So and certain more points regarding, I think, the internal energy and the Gibbs free energy. So because
Hello?
yeah,
Can you please repeat?
Yes.
Can you go to the previous slides, Gibbs free and internal energy?
Okay, sir. Sir, this one?
I cannot see. I can. Yeah. Okay, this is okay. Fine. Even the Gibbs free energy is fine. So it seems like you can see the values of alpha. Values of eta, whether it's positive or negative or 0, it determines how the black hole would end, right, in the quantum regime.
Mm-hmm.
So you can see the green and the red curve when the eta is positive. This means the positive corrections will lead the black hole to an unstable state and vice versa, right? So do you think you have
these correction parameters are only a numerical value?
Sure. I mean, there should be a physical picture what's going on there. Let's say it's purely arbitrary. It doesn't matter.
Yes, sir. Very right. As I think you are saying is very true here. Yeah.
I think we have dropped Vivek.
Srivastava?
Yes, sir. Hello.
Yes. Professor Masood, I think we got his answers. Maybe it needs more detailed discussions.
Yes.
So that
Yes.
you can contact with him with the emails that I shared in the chat. The questions you share are very important. I also give a concern to them. So thank you very much. Do we have other questions? I thank you. Do we have other questions from the other participants? If not, let's thank to Srivastava for his nice talk. And I want to continue with the talk.